So the last talk of this session is given by Ondřej Lengál on parameterized verification of quantum circuits.
Okay, thank you for the introduction, and welcome everybody to the first quantum talk of POPL'. We are still in the automata session, so if you came for automata, don't run away because there will be a lot of automata here. This is a joint work with several people. Some of them are in this room also. Yu-Fang, Chen, Jyun-Ao, and Ram are around, so if you're interested, just catch any of us, and we will be happy to talk about this work. So just a brief outline. So if you're not familiar with quantum, I will start with a very short introduction into quantum circuits. Then I will try to give you some general feeling of how the verification of quantum circuits look like. And then I will go for introducing our new formal automata and transducer models that we use for describing and reasoning about parameterized quantum circuits. So let's start with 101 on quantum circuits. So I guess you all have seen some classical circuits. So in a classical circuit, we have some wires, we have some gates. And if you want to talk about the state of a classical circuit, for example, at the end of this small circuit, then you can say, so the state is some assignment of 0 and 1s to the wire. So if you look at all the possible assignments of 0 and 1s to the wires, then the state in the classical circuit will be one line here will have the value 1. We are exactly in one state. In quantum circuits, this is a little bit more complicated. So quantum circuits, they look somehow similar to the classical circuits with some specialties, like all of the gates have the same number of inputs and outputs. Also, you cannot copy a state because of the no-cloning theorem and stuff like that. And here, the state of a quantum circuit is a little bit different. We are not in one state at the same time, but we can be in some superposition of states with some probabilities. So you can see here I'm in 4 possible states with an equal probability. But actually, I was lying a little bit. We don't have probabilities, but we have complex numbers. So we have complex numbers which are called amplitudes. Their probability that they represent is taken by taking the modulus of the complex number and squaring it. And of course, it needs to hold that all of the probabilities sum up to 1. So this is how a quantum state looks like. Let's look at what a quantum gate is. So for classical circuits, classical gate is just a truth table. You have seen this many times, I guess. For quantum circuits, a gate is a unitary. A unitary is a matrix such that its inverse is taken by its conjugate transpose. So not going into the textbook on linear algebra, this is just the thing that the gates are unitaries are telling you that everything is reversible, which is the property of quantum mechanics. You have no cloning, and you have norm preservation, which means you are not losing probabilities on the way. You still need to keep the sum of probabilities to be 1. OK, so you are now experts in quantum. And let's talk about parameterized quantum circuits. So what I showed before is just some normal quantum circuit. And I want to talk about parameterized quantum circuits, because many of the circuits given in the literature are parameterized by the number of qubits that you use. If you're coming from the quantum background, then usually people, when they talk about parameterization in quantum, they are talking about some rotation angles. The size of the circuits are the same, but the rotation angles inside the circuits are different. So what we are talking about is size parameterization. So we want to verify quantum circuits where the size is a parameter. And examples of these circuits, I said before, there are many of them. For example, generalized GHZ circuit, Bernstein-Vazirani, which is given in this example here. So you can see that the number of qubits here can be is arbitrary. We have these ellipses here, so we can put there more qubits. Grover's search is parameterized, error correction codes, arithmetic circuits, quantum counting, quantum phase estimation, which is the basis of Shor's algorithm, quantum Fourier transform, which is also used in Shor's algorithm. So all of these things are parameterized circuits. So let's go to the verification of quantum circuits. So how our framework works is that we are working with these Holík triples that you have seen many times because you're at POPL'. And in this case, the Holík triple, we have a C, which is for a circuit. And we have a set of states for a precondition and a set of states for a postcondition. In this case, the C is a parameterized quantum circuit. And the meaning is that if we execute C from some state which is in the set of in the precondition, then the obtained quantum state terminates in some state which is in the postcondition. So very similar to something to the classical Hall logic. A general approach how to do verification is that you can take some representation of the set of the precondition, of the set of quantum states in a precondition. You use some kind of abstract transformer, if I use the names from abstract interpretation, to compute the set of states after I run a circuit. You can do it by, for example, taking the whole unitary of the circuit and doing some matrix multiplication and stuff like that, or you can execute gate by gate. And in the end, you test this inclusion of what you obtain with respect to what is in the postcondition. Now the big thing is how to do this representation, because I'm talking about parameterized quantum circuits, and there are unboundedly many of them for some particular case, and we will need to be talking about infinite states of quantum states. So the quantum state that we want to represent, so I have a commonly occurring set of states, which is a uniform superposition. So this is a state which is used often in quantum computation. You usually start an algorithm by putting all of the qubits in a uniform superposition, and then you do some magic. So you need to be able to express the uniform superposition. This is essential for many quantum circuits. So you want to be able to express this. So these are vectors of complex numbers of the size, for example, 2, 4, 8, and so on. And if you look at the probabilities of these guys, so you need to take the modulus of this number and square it, then they sum up to 1. So this is for a set of quantum states. For the circuit, so we're talking about parameterized circuits, so you need to be able to express in some way an infinite family of circuits that look similar. So there is some example of some parameterized circuit that uses some common pattern. Like it starts by taking this kind of downward staircase using the U gate, then it's doing controlled not here, and then it's using this upward staircase using some gate W. And we want to have this representation such that we can test the inclusion of what we obtain after running the circuit with the states from the precondition and what we have in the postcondition. Now, let's go a little bit more to the automata side, which is regular model checking. So regular model checking is a popular approach for verification of parameterized classical systems. And there are many flavors of regular model checking. But in general, regular model checking is an approach for solving this question that I talked about before, when pre and post are represented by some kind of automata, and the circuit, or in general program, is represented by some kind of a transducer. Then the set of states obtained by running some system from some precondition is then obtained by taking the image computation of the transducer with respect to the precondition, and the inclusion is done by checking language inclusion on the automata. Now the question is, like, which automata and transducer models are suitable for reasoning about quantum states and circuits? So let's start by looking a little bit a different view of quantum states, which is that I want to persuade you that quantum states are actually trees. Why are there trees? This is the amplitude table I showed before. So what we can do is like push it a little bit on the top, it will fall down, and then we can build this nice tree on top of that. So you can, this is a tree, as it may look very similar to something like binary decision diagrams we have seen before. And it holds that for a quantum system with n qubits, you will have a tree which will have 2 to n leaves, and the tree will be perfect. So perfect tree means that all of the branches are the same length. So now if a quantum state is a tree, and I want to talk about sets of quantum states, so what is a good way for talking about set of trees? We are in the automata session, so it is some tree automata. So, but there are many flavors of tree automata, and let us look again at this uniform superposition set of states, which is useful in quantum computation, and which tree automata model should I take to express this thing. So I want to express trees that look like this, a set of trees that looks like this. And if I look at the standard tree automata, then they have a problem that they are very regular. So regular means local, so it means that I cannot really synchronize these sizes of the tree. So I cannot, using tree automata, I cannot have perfect trees, because if I'm looking at a run of a tree automaton through the tree, I go to the left, I go to the right, and these two branches are completely independent. So I have no way to express perfect trees in using standard tree automata. So last year at POPL, we introduced a new automata model called level synchronized tree automata, which has some synchronization over, which has some global synchronization over the levels, which is able to express perfect trees, but it cannot express unboundedly many amplitudes. So what we need here, if we want to express the set of all possible superpositions, we need unboundedly many amplitudes. The problem with the level synchronized tree automata is that we still have a finite number of leaf symbols, so we cannot express these things. So let's talk about our new formal model called synchronized weighted tree automata. So how does it look like? So for simplicity, I will not talk about internal labels of trees. We have them, but for the presentation, I will avoid them. So the automaton is a 5-tuple. We have a set of states, which is standard. It is finite set of states, similar as the finite automata. We have this omega, which is a set of colors or choices, which are used for synchronization. We have a transition function, which I will describe later. We have one root state, and we have a set of leaf states. And the automaton accepts the tree by starting at the root of the tree from the root state. It goes down, and in order to finish branches, it needs to come to some leaf state. I will describe this semantics in more detail later. So in this synchronized weighted tree automata, we have the standard tree automata, but we put there two more things. The first thing is the synchronization, which is something that we already had in the previous model, but let me describe it in short. So if you look at the standard tree automata without any synchronization, so we have a root state Q, which can make these two transitions. It can go down to QQ, or it can go down to UU, and U is a leaf state. Then it can accept these trees, and you can see that some of these trees are nice, but some of them are not nice because they are not perfect. For example, this tree here is not perfect because one subtree is smaller than the other one, also this one, also this one. So these trees are not perfect, so this is a problem with using standard tree automata. If we have a synchronization, so the synchronization works by labeling transitions by some of the colors. And then there is a property that if you look at the run of the automaton on a tree, that at every level of the tree, the colors of the transitions taken by the automaton needs to be the same. So if you're at some level, so let me show you a picture. So if you're at some level, you need to, all of the colors at some level need to match. So this needs to be the same thing. And this allows you, for example, to express the set of perfect trees. So this is one of the very interesting and important set of quantum states. You can use this to express the computational basis states. So these are all the classical states where there is no superposition. So this is just the classical states. And the LSTAs can be used to express this, but they cannot be used to express the uniform superposition states because, as I said before, we need an unbounded number of amplitudes. And that's a problem here. So we need to introduce something more. And the something more is weightedness, that now the states are given, or the transitions are given weights. And the transitions now look a little bit more like this. So you can see that now, in addition to the previous thing, I have some weights here in the transitions. And these weights are telling us, if I look at the tree automaton as a generator of something, that I go down the tree, I start in the root state, I go down the tree, and if I go down the level with some weight, then I keep multiplying the weights on the branches. So you can see that I label the tree with some weights on branches, and then if I finish in a leaf, I just multiply everything which is on the branch. So this concrete automaton can be used to express this set of uniform superposition states. And in general, we need to have a little bit more general form of the transition. So we don't only have weights, but we have some kind of linear forms here and also here on the left side and also on the right side, which are telling us that we need to combine some different runs of the automaton. So the semantics, if we look at it as a generator of this transition, is that I will, if I'm in U and I want to take this transition, I start by inductively taking a tree which would be generated by P, taking a tree which would be generated by Q, multiplying each of them with the corresponding coefficient. By multiplying, I mean I go to the leaves and I multiply all of the leaves there with the given value. I will sum them together, for which they need to have the same structure. So I'm only talking about the perfect trees which have the same height. And then this will give me the tree for the left side. I will do the same thing for the right side. And there I will construct the final tree by just taking the left tree, right tree, and taking one node as their root. The language of this automaton is then given as usual. It's just a set of trees that are generated by A. So what are the properties of these automata? So language union, the model is closed for language union. The proof is very simple. You just merge the transitions together. You may need to relabel some choices, but that's easy. Language complement, they are not closed, and how to show that they are not closed under the language complement, that's very simple, because if you just look at the number of possible trees that have complex values in the leaves, then there are uncountably many of them, so you definitely cannot express that. What is nice is that language emptiness is p-space complete, so it's decidable, it's p-space complete. The membership is done by just quite simple subset construction, which is just keeping the track of the frontier of the states, and the hardness is done by a reduction from finite automata universality. But these are pretty much like all the nice things, because we have intersection non-emptiness, which is undecidable, because we can encode PCP into it. So this is the first undecidable problem. From this, it follows that language intersection is that we don't have closure under a language intersection. Why? Because we know that emptiness is decidable, but we have undecidable intersection on emptiness. And language and equivalence, language inclusion and equivalence is also undecidable, for which we have a proof from reduction from emptiness of a Turing machine. So this inclusion and equivalence undecidability is a kind of bad thing, because we need to do this when we are checking, when we run our algorithm, we're checking that the states that we obtained are a subset of the postcondition. So this is bad. So this seems like, okay, so this is a nice model, but it's actually not useful because we cannot use it for verifying quantum circuits. But actually, we have an alternative, and the alternative is do not talk about the language of the automaton. Let's look at something else, and what we have is we talk about the tree function of an automaton. Because as I said before, we have these kind of synchronization colors, and we can see an automaton to be a mapping from sequences of these colors into trees. So you can see as a tree function of the automaton, we take sequence of colors into trees, and example how this look like is, for example, for some automaton, it can represent that a mapping from 112 into this tree of the uniform superposition. So you can see the automaton as a function from trees, from sequences of colors to trees. And this is very useful because because what we can do is that for every computational basis state, which we often need to talk about in a quantum verification, we can have a one-to-one mapping into a tree, into a color and into the sequence of colors, and that gives us a mapping into a tree. And also that when we compute the image, we preserve this mapping of sequences of colors to trees along this computation. So this gives us a power to do relational verification. What we can do is that we can verify that if we started from one quantum state, we came to a different quantum state. We don't have this like a mix-up of, we don't know, if we look at the postcondition, we don't know what the resulting quantum states originated from. So we have this kind of relational property that we have in our verification. And this is very powerful because we can actually, seems that we can actually do more than we would be able to do if we just check for the language inclusion. And we can also use this for showing doing circuit equivalence checking. Because for doing circuit equivalence checking, we just need to, if we have two circuits, we just need to start both of them with the computational basis states. There are like 2 to n, many of them. And we can look at the automata we obtain as the results of the computation, and we can check functional equivalence of the automata. And if functional equivalence holds, then we know that the circuits are equivalent because they are encoding unitaries, and by linearity, we know that we only need to check if we have a unitary with dimension n, we can only check like n many independent vectors. So this tree function is a very useful thing, as I try to persuade you. And we also have a tree. So the questions we are worried about are tree function equivalence and inclusion. So we want to check that the tree functions of two SWTAs are the same, or they are at least included. And the question is, well, how to do this now? So we took a different problem, but is the problem actually solvable? Because the original inclusion wasn't. So the good thing that it is solvable. It is p-space hard, and it is in X time. And the interesting thing is how to show so what is the algorithm? So how to decide this? So if I want to show the algorithm for the tree function equivalence of two automata, the first thing what I do is that I check the equivalence of their domains. And this is easy because as I said, they are mapping sequences of colors into trees, so the domains are some sequences of colors which can be expressed by some finite automata. So first thing is we take the domain DFAs of these two automata. We check whether they are the same. If they are not the same, we know that the functions are different, so we can terminate here. Otherwise, we compute the automaton which represents the minus of these two SWTAs. So the minus means I have an automaton that will represent the trees which are obtained by taking the two trees for the particular word of choices and doing minus of them. And then I can check that what I obtain, the automaton generates only 0 trees. And this can be done by transforming the obtained automaton into a linear transition system. So this is a finite system when I have a bounded number of complex variables, and I have linear updates of edges. And I'm wondering what's happening in this system. So we want to check that we only obtain, at some interesting states, we only obtain zeros, the result of zeros of doing this linear updates, which can be done by running the famous Cars algorithm. So if you don't know about Cars algorithm, this is an algorithm that takes the linear transition system and deduces all affine relations between the variables in the systems. This is a very nice algorithm. I recommend you to look at it if you don't know it. Very quickly, weighted tree transducers. So we have a regular model checking approach. We have automata, and we also need to have transducers. So we also introduce a corresponding tree transducer model. So it looks very similar to the automata. For the sake of time, I will only show the transitions, which look also similar, with the new thing that we have left here and R here, which means left and right subtree, because transducer needs to take a tree and convert it into a new tree. And these transducers are very nice because we can have a compact representation of parameterized gates by transducers. Before we were using some specialized procedures, which was not so nice. Composition is quadratic, image computation is quadratic, equivalence inclusion checking is X-time complete. So this is a very useful model. Okay, and we also have a way how to obtain these transducers for parameterized circuits automatically for some patterns. So for example, for the Hadamard transform, we have this very simple transducers, which is doing this uniform superposition. And for some more general patterns, we have a way how to obtain a transducer that can do this kind of behavior of some fixed-sized gate. So let me go to evaluation. So we implemented this in some C++ prototype, and we tried to verify several circuits, Bernstein-Vazirani algorithm, carry ripple adder, some syndrome extraction, and quantum error correction. And also equivalence checking of two classes of circuits, Grover's algorithm, Hamiltonian simulation, where we are checking equivalence of optimized and non-optimized circuits. And you can see that in many times we managed to verify the circuits under 1 second. The hardest problem was this adder, which is strange because it's not a quantum circuit. In principle, it's just a reversible classical circuit, but it has some complicated structure of what's happening there. So the transducers there were getting quite a big, so it took the longest time. To conclude, so I introduced a new automata and transducer model, which is very interesting for capturing parameterized quantum circuits. It is expressive, but we still have decidable this tree function equivalence and inclusion property, which allows fully automated verification. And for future work, we have some ideas how to extend this model with recursion, because what we want to do is quantum Fourier transformation. That is a very important algorithm in quantum, and we want to have a parameterized version of it. And we want to also work a little bit on the engineering side to have some fully automatic conversion for open QASM files. And the next thing also is support for measurement. So before I finish, this is automata session. Quantum and automata are a very good match. I try to show that now. And if you're working in automata and you would like to also try the flavor of quantum, please try. It is very interesting. There are very interesting problems there. And let me end with that. Thank you.
Time for one quick question.
Yeah, thank you for the talk. So in general, we use projections as predicates for preconditions and postconditions, but I saw that here you're using sets of states. Mm-hmm. So how would this change if you considered projections instead of just sets of ensembles?
Yeah, so this is, so you're talking about like quantum Horo logic, right?
Yeah, pretty much.
Yeah, so I think we are incomparable with quantum Horo logic, so it is a different approach. We're thinking about how to combine them together, and I think it's something for future work.
Okay, sounds good. And how would this verification look when you have like noisy circuits?
We don't consider that. We just look at the very fine ideal circuits.
Thank you.
There was another quick question, maybe?
Thank you for the amazing talk. I noticed that the test case for Bernstein-Vazirani had a fixed secret. Mm-hmm. How would could this formalism deal with unknown secrets and a given oracle? Like, for example, for Deutsch-Josa, if you had an oracle for f of x, could this deal with any f of x with the promise of half and half?
Yeah. Okay, so that's a very good question. So in this example I have for Bernstein-Vazirani, the secret is somehow fixed. It's parametric, but it's fixed. We have a ways how to do it for also any secret. So for that, we need to somehow generalize the oracle. It's possible, but we can do it manually. But in general, we come to the problem of it depends on how you really write down the precondition and postcondition. But we came to the problem of that we need to do language inclusion. And in the case where we have more than one choice, the language inclusion is already undecidable. So we could do it manually by doing some kind of minimization of the automaton and then just showing isomorphism. But we don't have like a complete procedure for this case. But I think that it should not be difficult to do it.
Great, thank you very much.
Okay, let's thank Ondřej again.